before looking at the demo, we will quickly see our previous we'll see our previous code which we have written in our EDA playground. Okay, so here we will see that this assigned statements, first of all, we see that these are all happening in parallel. So what does it mean? That whenever PC1 is evaluated, and as soon as PC1 is evaluated, then this PC1 is now modified here, then you will see PC4 value getting modified after 1 unit of time. So this is happening continuously. There is no sensitivity list. There is no @ statement which says there is an event which has occurred. So because all of these things are happening continuously. Now this was the delay part here. Now let's see this delay part also. So if you see here, initial is being written. Initial means time equal to 0. So after this statement has been assigned, after these 3 assignments has been done, they would be done instantaneously. Then after that there is a delay of 20 units of time. So after that, for 20 units of time, there is nothing which is happening. And after, because these are all blocking statements, so once these are done after 20 units of time, then after these statements are over, then only we will start with the next set of statements. Okay, so this is how our blocking statements were working. So we were going only statement by statement, and assignments were happening only when these assignments have happened. Then we'll come to this next set of assignment, and that's how your test bench was working. So the orientation of our test bench was that we first give first set of inputs, then wait for 20 units of time, and then give the second set of inputs. So we wanted itself to be blocking and sequential in nature, that these things should not happen in parallel. If they are happening in parallel, then it's not would not perform the task of our test bench. Okay, so let's quickly simulate to see this timing effects also within the full adder. So if we see, let's run, and so we would like to see any particular full adder, let's say the first one, or any full adder we can see. So maybe I can delete all of these, and then we can start afresh. There is no way to delete all of these signals at the same time, so we have to delete them individually. Let's hope it doesn't take too much of time. So meeting. Okay, so let us get the signal for one particular full adder, and all of the signals we'll try to see. And yes, and we'll also try to make it little bigger so that we can observe some changes. So you see that your input, this is your test Cin. So input has been, we have seen the input here. Where is the input change? Yeah, input changes A and B. So for this particular adder, probably this, because A means in the end there is a 0, D also means in the end there is a 0, so it is not impacting this particular adder, but your PC1 is changing after 1 unit of time. So after 1 unit of time, you will see a change in PC, and that would be reflected in sum after 1 unit of time. Okay, so this is how things are happening continuously. And you see here also, so your input was assigned here. So after 1 unit of time, we see there is a change in PC1 as well as PC2. And then after 1 unit of time, you have a change in PC4. And because there was a change in PC4, you also see there is a, because my sum will get modified only after 2 milliseconds, two units of time, and after another 2 units of time, it again further get modified, because the sum was written as a set of two XOR statements. So this is the impact of first XOR, and this is the impact of the second XOR. So that's how this continuous evaluation is trying, it would be reflected here in the timing diagram also, that the signals would be changed as soon as the previous signal has changed. So this was about the continuous assignment. And similarly, you have seen, anyway, observed that inputs are changing only after 20 units of time. So this was, and this was being done in our previous, and you also have observed that this reg was assigned whenever we are writing anything within this initial block. If we are not writing those things, we are still defining as wires. Okay, so now let's look at the implementation of this 1011 overlapping pattern. So let us start with the very low code. In the very low code, like a similar places, we also have a clock signal. Additionally, other than D in and D out, there is also a reset signal. So what is this reset? Reset is a important signal which will try to distinguish our whole like hardware in divided into two parts. One is the initialization and the non-initialization part, or actual running part. So in when a reset initial after at initial reset, so once we have initialized the states or initialize our variables, then after that they can take on you know these. There could be one comment that why don't we use this initial block. So this initial block is non-synthesizable block. It doesn't get synthesized. We cannot synthesize that in as form of hardware. So initial block is always present in your test bench, not in your design. In your design, if we have to bring some functionality of initial, that means some part that would be done only single time, one time, then we define a reset signal. And in the test bench, and actually in the real life also, we will make sure that reset would be applied only once when the system is about to start. After system has started, then reset is not being employed because system is running. So it is always there in some state. So and you will see that even whenever you buy any electronic gadget, there would be some reset pin defined at some places. So in mobile phone, it would be somewhere internally, which will say that do a hardware flush, everything would be reset. It so in similarly in any other electronic device, there has to be a reset pin which will say that now things will start from the scratch. Okay, so now there's also we'll see that these are the input, D in and D out are the inputs. So we, like regular, we have defined them as input clock, input reset, input D in, and output as D out. Now we have again defined this D out as reg. So we'll talk about it in a minute, but let's see the rest of the things. So here by defining it as an enum type, we are saying S0 is 0, 0, S1 is 0, 1, S1 is S2 is 1, 0, and S3 is 1, 1. So essentially, in some way, we are defining the state encoding right here. Okay, and state minimizations and those things would be either done by a compiler, depends on its optimization level. Sometimes it may not be done. Okay, so the next is, because all of those things would happen at the active edge of your clock, so we have to write a always block, and in always block the event would be positive edge of your clock. In addition, we are also writing or positive edge of reset. That means whenever either of these events will occur, this always block will get triggered. So the reset part is only this, that if positive edge of the reset, that means when a reset is going from 0 to 1, then we are assigning d out equal to 0, and we are also assigning our initial state. So initial state has been decided based on the reset. After that, you see, we don't care when reset have come down, whether it have come down or not. And also we'll try to make sure from the user side that it is the rising edge, positive edge of the reset will come only once in the duration of our test bench, unless it is required to be reset again. Okay, so rest of the things are like representing our state diagram here in terms of a statements. We are saying case statement whenever we are in S0. If it is D in, the next state is S1, D out, my output is 0. So if we see it here, so we can close this. We can also close this. So now you can see that when my state is S0, if input is 0, then the next state is again S0. So that means we don't do anything. And if input is 1, then we are moving to state S1 and output is 0. So here also we are saying output is 0, but we are not changing the state. So that's why the second statement is not there. If we are in S1 state, if input is 0, then if input is 0, we are going to S2 state. If input is 0, D in is 0, then we are going to S2 state, and the output is D out is 0. And else, else means we are again in the same state, so we are simply writing the output is 0, D out equal to 0. Now, if we are in S2 state, similarly, we are saying that if input is 0, then the next state is going to be S0, output is 0. And else, that means my D in is 1, then next state is S3, my output is 0. So it is very similar to, we can keep our state diagram in front of us, and then we can keep on populating this. So one observation here, you can see this is a syntactical observation, syntax observation, that whenever there are more than one statement in if, then we are writing begin and end. If there is only single statement, then we are not writing begin and end. Okay, so here in the state there were only 4 cases, so that's why case S0, S1, S2 and S3 are there, and there is no default case, so that's why we are simply ending the case here, and that's the module here. So this is the this is how we can use this behavior modeling to define the state machine, to implement the state machine. Now let's quickly look at the test bench part. So in test bench also, yeah, one thing we forgot. So while register here, so you see that while discussing theory part, we see that whenever there is a always and we are writing something, here we are writing 2 things. We are writing D out, we are writing state. So now D out is otherwise defined as a module output. And as a module output, we have defined is as a output port. Now, along with the output port, we have to specify it clearly that it will also require some additional storage so that it can store intermediate values. That's why we have to redefine this D out as a register. Okay, and because this state is defined as a bit type, so it is already a kind of a register. So anything we write in our always block will have to be a register. That's why we have redefined our output as register. Now let's look at the test bench. In test bench, we are doing the same thing. Like we have whatever we are writing, we are making them as register, test clock, test d in, and test reset. And test d out is a wire. And yeah, so this is also an interesting block where we are saying always #10 test clock equal to not of test clock. So this way we are creating a test clock. We are creating a clock signal which has a frequency of, which has a time period of 20 units of time. Okay, and this will get triggered automatically all the time. Okay. So and also it would happen in parallel to all others. So now we have instantiated our FSM, and after instantiation of FSM, our initial block is starting. In the starting of initial block, we are assigning test clock equal to 0, reset also equal to 0. Now, this is how we are trying to define our rising edge. So at 5 units of time, first reset is made 1, and then after 10 nanoseconds, 10 units of time after this reset is 1, then it is pulled down. Then your and then we are trying to generate a directed pattern. So in directed pattern, we are for every post edge, for every positive edge, we are writing every post edge of our clock. We are writing a blocking statement of test d in equal to 1, 0, 1, 1. So this way, one pattern would complete here, and then again 1, 0, 1, 1. So this is another overlapping pattern which will finish, and then 1, 0, 1, 1. So this is the another pattern that would be there. So to make it complete, we have also added some random numbers. So in random numbers, we have again used the same test at every post edge. We are assigning this random values to our test D. And one more interesting statement which was not there, which we were not required to use in our previous test benches, was this finish statement. Okay, so in finish, actually, let's not use this finish, and let's see what would happen. This was probably copied from somewhere else. Now let's run it, and we'll see a couple of things, and we'll see a couple of more errors also. Now let's comment out this also. Now when we run, it says that lot of errors. Error is saying D out is not a valid L type in tb.dot. So in design.sv line number 14, there is an error that D out is not a valid L value. So means we know the meaning of this error. L value means that you cannot write 0 to D out. Why we can't write? We have defined it as output. That means we can write. But because this particular statement is inside a always block, it requires that the data type D out must be of a register type or integer type. Now, when we define it as a register type, then it works. That means, yeah, there is no error, but it is also not stopping. It is not stopping. Why? Because there is no finished statement. Okay, so but there was no write here also. It was not coming continuously after 290. After this 450 units of time, there was no statement also, because there was test D in was not changing. So what was happening in our previous test benches where we were not using this hash finish, dollar finish. So Verilog simulator will automatically finish when there is no further transitions. If there is no change in the signal, then it will automatically say. So in other words, when it says that the pending list of signal changes, if it is 0, then it will finish automatically. But here we have one statement which is continuous and which will never finish. That is the rate always #10. Okay, so if we say instead of saying always, we call it a repeat statement, then possibly it will work, repeat for n number of times. But here, because it's a always statement, this means that your Verilog test bench is always generating some event. So we have to explicitly kill it. So for explicit killing, we sometimes specify a particular time when we have to finish our simulation. So that's why 100 hash 100, that means that 100 time we have to finish. That's what is being written over here. So now you will see that we see a clock, and reset was initialized only for a certain time, but clock was there initially. So at the each positive edge, we were changing some values of D in. It was first 1, then 0, then 1. Even if we increase the resolution, because there was no other delay involved, so it is always happening at the same time as our clock is changing. So after this pattern of 1 0 1 1, my output become 1. Similarly 1 0 1 1, this is a repeat pattern, overlapping pattern. Again I observe this as 1. So another pattern of 1 0 1 1 again yield me test out as 1. Now these are all random inputs, and in the random inputs also we observe some of these patterns. 1 0 1 1, we see 1 here, and similarly 1 0 1 1, we see an output of 1. So we can also observe that states are moving from 0 1 2 3, and again 1 2 3, and so on and so forth. So with this we can possibly conclude our session. We have learned a couple of new things today. In case of Verilog also, we have seen how behavior modeling works and how different syntax, what are the limitations of these syntaxes in behavior model, and how we can use @ signals sensitivity list. That's what we have seen. So as we would require, so tomorrow we'll take little more complex example, and we'll see that how that can be designed using Verilog. Okay, so with this I will stop my presentation. I would be open to questions.